Okay, so for homework 3, part C, we're going to be deriving an expression relating the flow rate of fluid and location of a spherical ball in a rotometer tube. The bottom of the rotometer has the same diameter as the ball and has a linear taper of slope d equals mh plus d, where little d is diameter of the tube. Um, so, to start us off, um, we're going to, we have those assumptions that we have, which is the flow from the annulus between the ball and the wall to the region past the ball is assumed to be sudden expansion and there's no pressure recovery. And then there's viscous effects. Viscous effects and losses due to sudden contraction in front of the ball are negligible. So, let's draw our rotometer tube, which is going to be like this, with a spherical ball on the inside. That's an awful circle. Spherical ball on the inside. The bottom is going to have diameter d. Going downward is going to be positive. This slope here, let's do it in a different color. Slope and m, which is equal, yeah, so this is our slope, right, sorry. But for that we have d equals m times h plus d. So then our slope is equivalent to divided by h. So d plus d over h should be. So we're going again to derive an expression relating flow rate and location of ball, which is going to be our q and h. So if we have Bernoulli's equation, which we can relate between 2 points along the streamline, which is going to be down at the bottom here, and then in the middle of the ball, we're going to have P1 plus 1/2 rho V1 squared plus rho GH1, which is going to be equivalent to P2 plus 1/2 rho V2 squared plus rho GH2. So we're going to apply Bernoulli's equation between 2 points, which just, oh, sorry, my line's wrong. Well, we can fix that. So we're going to apply it just before the ball and then just after the ball here. So this is going to be P1, that's going to be P2, and P1 is going to be equal to P0 plus rho GH, and V1 is going to be equal to 0, and then just after the ball is going to be P2, and it's going to be equal to 0 since the flow is assumed to be fully developed after the ball, and then our V2 is going to be equal to V, which is going to be the velocity of the fluid. So we can neglect the difference in pressure, which is P0, because between the 2 points, because it cancels out, so we don't need that. And then the height difference, which is h2 minus h1, is simply the diameter of the ball. And then the velocity v2 can be related to the flow rate, which is q, using the continuity equation. Sorry, can't talk. So this equation states that mass flow rate is conserved in steady state flow, which is m dot, so it would be m dot 1 is equal to m dot 2, which is equivalent to saying that a1 v1 is equal to a2 v2, which we can break this down even further. Hang on, move this up here because that equals that, and then it can be that pi d2 squared times 0, because there's no velocity, is equivalent to pi d over 2 squared times v. So then this, you would just get that v is equivalent to 0. So given that there is no velocity just after the ball, we're going to be left with rho g d is equivalent to rho v squared over 2. So then plugging in some previous expressions found in things, we're going to have rho gd is equal to rho q squared over pi times d over 2 squared times 2. And then solving this in terms of q, we are going to get that q is equivalent to pi d squared over 8 square root of that times the square root of 2gh over 1 over n minus 1. So this is going to be, this right here is going to be our expression for the flow rate in terms of location of the ball, which is h, in the rotometer tube. So